Hello, this is Aliag and I'll be the one presenting our work regarding the effect of temporal subsampling methodologies on the accuracy of quality evaluation of volumetric video content. It's a collaborative work between me, Sui Ling, and Patrick Lecalais from University of Nantes, and Emin Zerman and Alyosha Smolic from Trinity College Dublin. Recent advancements in acquisition and display technologies brought popularity to immersive media formats. One of them is volumetric videos, which allows to capture 3D objects in real world and display them from every possible angle to the viewer. By capturing spatial and temporal information in the 3D space, viewers can take advantage of a more immersive experience than the traditional 2D image or video content. Volumetric video is captured in dedicated studios with many surrounding cameras. These cameras capture real worlds synchronously, and the 3D object is reconstructed as volumetric video. The captured sequences can be reconstructed and represented as 3D meshes or point clouds. 3D meshes contain vertices, edges with connectivity information for geometrical features, and uses texture maps for color features. On the other hand, point clouds does not store any connectivity information and represent each point individually in the 3D space. Therefore, it allows a simpler compression and transmission scheme. Although both representations have their benefits depending on the task, nowadays point clouds attract the signal processing community due to its simpler representation. Due to high dimensionality of the data, compression plays a crucial role in volumetric video imaging pipeline. State-of-the-art coding algorithms can be used to compress point clouds to allow easier transmission by lowering the bitrate. However, it comes with a loss in perceived visual quality. Therefore, it is important to balance this trade-off. In order to do so, quality of the compressed content needs to be measured. By nature, quality is very subjective, and conducting user studies is the ultimate way to measure the visual quality. However, these user studies are both time and resource expensive. Alternatively, objective quality assessment metrics can be used to measure the perceived visual quality. Although the accuracy of the metrics needs to be ensured, they provide a less costly solution. Current challenge for objective quality assessment of volumetric videos come from the large amount of data stored for a single volumetric video content. It results in time-consuming calculations to measure a single quality level. Therefore, in this work, we seek an answer to this question: can we speed up the metric computation without sacrificing the accuracy? To do so, we analyze the effect of temporal pooling methodologies and temporal subsampling rate on the metric performances. We also provide a benchmark of 30 objective quality metrics on volumetric video quality assessment. Objective quality metrics for volumetric video content can broadly be split into three categories, as point, color, and image-based. Point-based metrics measure the quality of a distorted sequence in regard to the non-distorted sequence by comparing the geometric information of each point at each frame. Color-based metrics also uses the color information of each point at each frame for quality assessment, in addition to the geometric information. And finally, image-based metrics compare the rendering of each frame of the volumetric video content. In our experiments, we considered 13 point-based, 6 color-based, and 11 image-based metrics, and we end up with 30 metrics in total. As previously described, volumetric videos contain multiple frames. Objective quality metric assesses the objective quality of a sequence frame by frame. Then the quality score of each frame can be pulled temporally into a final quality score with a predefined pooling function. We evaluate the metric performances with varying temporal pooling methods under varying temporal subsampling rates. Noting that the frame rate of the undistorted volumetric videos in our experiment is 30 fps, we experiment with 8 different frame rates. We uniformly sample the frames by starting from the first frame and ending with the last frame at all times. Additionally, we experiment with 7 different pooling methods from the literature. Details regarding the pooling methods can be found at the paper. We conducted our experiments on the vSense VVDB2 dataset. It contains 8 point cloud sequences of 10 seconds with 30 fps. All sequences compressed with 3 state-of-the-art coding algorithms, resulting in 16 compression levels in total. A user study later conducted with orbital rendering of each sequence. They are displayed on a traditional 2D display with ACR-HR methodology in order to collect mean opinion scores from the participants. We start our analysis by investigating the effect of temporal subsampling rate on the metric scores. We select the XGI stimuli as a reference and evaluated the quality of 5 sequences which encoded with VPCC coding algorithm. Here, median values and the 95 percentiles of the 4 selected metric scores are plotted with 8 different frame rates. On each plot, vertical axis is the metric score and horizontal axis corresponds to the indicated frame rates. While for higher performing metrics, namely color Y and SSIM, metric scores do not change along with the temporal subsampling rates. However, lower performing metrics, EMIQM and point-to-plane house scores fluctuate considerably with varying frame rates. Similarly, we plot all the median metric scores for 16 different compressed versions of the same stimuli. It can be observed that most of the metric scores are not affected from the temporal sampling frequency differences. After observing the slight change in the metric scores, we evaluated the metric performances with Pearson correlation coefficient as recommended by ITU standards. Here, metrics are divided into their corresponding categories, and for each category, Pearson correlation coefficient values of the best performing metric is displayed with a bold font. Expectedly, Pearson correlation coefficient values of the higher performing metrics stay the same even with frame rates as low as 1. This suggests that the low subsampling rate can be used to decrease the time spent on objective quality metric prediction down to 3.3% of the full frame rate calculations. Evaluation of the metric performances in terms of Spearman rank order correlation coefficient and RMSE can be found in the supplementary PDF file. Link to the supplementary PDF is given in the paper. In order to measure the impact of temporal pooling method on the metric scores, we plotted the selected metric scores of the 128 point cloud stimuli from vSense VVDB2 dataset in comparison to their demos. Horizontal axis in each plot is the predicted score of the corresponding metric, and vertical axis is the difference mean opinion score, or shortly DMOS. Each point belongs to a unique stimuli in vSense VVDB2 dataset, and there are 128 of them in total. Similar to the temporal subsampling analysis, higher performing metric scores, SSIM and color Y, do not vary greatly with different pooling methods. On the contrary, lower performing metric scores show greater change with various pooling methods. We calculated the Pearson correlation coefficient values for each metric with a fixed frame rate of 30 fps and with varying pooling methods. Again, metrics are divided into their corresponding categories, and for each category, PCC values of the best performing metric is displayed with a bold font. In the table, it's obvious that the change of temporal pooling method does not affect the higher performing quality metrics. We cannot observe any pattern which favors a certain pooling method over another. Again, Spearman rank order correlation coefficient and RMSE values for this analysis can be found in the supplementary materials. Finally, we present the result of analysis on the combined effect of temporal pooling method and subsampling rates. Yellow color indicates higher PCC value, while blue color represents the lower PCC values. Each row corresponds to a certain metric which has the same order in the previously shown tables. Columns are divided into 7 for each pooling method, and then each pooling method further divided into 8 columns for the tested frame rates. As can be seen from the heat map, we can further confirm that there is no clear advantage for any of the pooling methods over any sampling frequency. To conclude, results show the temporal subsampling has minimal effect on metrics correlations with ground truth subjective scores for point cloud compression artifacts. Each considered pooling method has a different priority for the temporal dimension and result in minimal change in metric performances. Our findings suggest that with no significant loss in the accuracy of both types of objective quality metrics, calculations can be sped up to 30 times. Further research is required to further extend the current conclusions for the other type of distortions. Thank you for your attention. We will be with you soon to receive your questions.